and this, and this, and this, and that's all I wanted to have happen. 7 minutes later, and this big old scary thing with my face on it, and now we're back. Okay, all right, so guys, again, Friday the 7th, right? So here's how this goes. This is Orem High School, okay? 2:15, I'm headed north, and I am going to drive 5 miles to my house in Linden. I'm going to pick up my son. That's my house in Linden. Then I'm going to drive 30 miles, and I'm going to pick up my father-in-law who lives up in Holiday. Then from there, I'm going to drive 65 miles up to Corinne, Utah. Now the problem is once I hit Corinne, I've got to go west, and then I've got to backtrack another 5 miles to get to the place where we hunt ducks. Okay? Here's the question. How far is it from Orem High to that place? No. Yes, as a duck fly. Not bad. How far is it from here to there? And I don't mean what distance did I travel. I mean how many miles is it from Orem High to where we duck hunt? So we've got 5 and 30 is 35. We add to that 65, we get 100, but then we backtrack 5 miles, so this whole trip is 95. You get the idea? Guys, you can do the same thing with chemical reactions. The idea is if you know a chemical reaction, and if you can break it down into a series of steps, by adding up those steps, you can figure out the overall energy for the reaction. But guys, notice that direction matters. When we think about driving a car, we think about, in this case, north and south. And if driving north is the overall distance, any direction, any south driving we go, decreases the overall distance. We know it really doesn't decrease the distance traveled. That's where the analogy breaks apart. But guys, what does this idea of distance have to do with energies of reactions? We've got positive and negative. North was positive, south was negative. When we think positive and negative in chemical reactions with energies, what are we thinking about? Endo and exothermic. Do you get the idea? So guys, if we have a reaction switching to blue, and if these are the reactants, and if this reaction goes through 3 steps, and then a 4th step which goes this way, A, B, and C. Get it? This is like an energy diagram. Guys, A, B, and C, endo or exothermic. Endothermic because energy is going up. This could be 5 joules, 30 joules, and 65 joules. Then this step over here, D, is exothermic. So what is the total energy change for the reaction? 95 joules, in the same way that the distance traveled was 95 miles, because we've got 100 joules of energy going in, 5 joules of energy coming out, and so the net change, the delta H, if you will, for this reaction would be plus 95 joules. Does that make sense? Okay, guys, that's Hess's law. That's all there is to it. Is if you want to study this chemical reaction, which is reactants to products like Orem High to the Duck Club, guys, that's the overall reaction. If we know the steps that it takes to get from one to the other, the beginning, the reactants, the ending, the products, then we can add those all up and get the overall energy for the reaction. That's Hess's law. Does that make sense? You okay? Okay. So guys, if that makes sense, then the question becomes, where do we get the numbers to add up in order to get from one place to the other? And guys, this is where we run into these 2 ideas. This can either happen, you don't need to write this down, you've already got it in your notes. This is the bottom of the flow chart. This can either happen through manipulation or it can happen through computation. So guys, we're going to do manipulation first, then we're going to link this to Hess's law, then we're going to do computation, and you're going to find out that they're actually very, very closely related. You ready to go? Okay, manipulation first. Write this down with me. Here we go. All right, so here's what we know, guys. We have got a chemical reaction. And actually, you don't need to write this part down. This is what this will look like on the test. Just trust me about not writing this down. So guys, you'll see something on a test and it says the enthalpy of combustion when carbon turns into carbon dioxide is negative 393 kilojoules per mole of carbon, and the enthalpy of combustion of carbon monoxide to carbon dioxide is this many kilojoules per mole of carbon monoxide. Now guys, breaking this apart, first of all, what do we know because both of these are negative? They are both exothermic. So when carbon turns into carbon dioxide, is energy given off or taken in? Given off. When carbon monoxide turns into carbon dioxide, energy in or out? Out. Both exothermic. So guys, you will see something like this on the test where they'll give you an introduction to the question, but then what they'll do is they will give you these in equation form. Aha! Now guys, let's talk. First of all, do you understand that these are these in equation form? So carbon here plus oxygen makes carbon dioxide, and here's the amount of energy that's released per mole of carbon, but this balances with 1 mole of carbon. You see that? Okay, now let's look at the next one. So it says the enthalpy of combustion of carbon monoxide to carbon dioxide is this per 1 mole of carbon monoxide. So guys, remember that when we have thermochemical equations, the values are for the number of moles represented. So this has got to balance with a 1 in front of the carbon monoxide. But here's the problem. If we tried to balance this, we'd go 1 carbon, 1 oxygen, 2 oxygens, and then that would actually be 3 oxygens. So if we had CO plus O2 yields CO2 and we wanted to balance that, in order to balance that, remember we've got the odd-even conflict, so we'd have to put a 2 here, and then that would give us 2 carbons, and now we've got 2 carbons, 2 oxygens, plus 2 oxygens is 4, and that's balanced, right? But the problem is if we balance it like that, then this is no longer true. You see what I'm saying? Because this is no longer 1 mole of carbon monoxide, it's 2 moles of carbon monoxide, which then makes this number wrong. How could we fix that number to make it match this equation? Double it, right? But instead of doubling it, guys, what we do is this. We divide everything by 2. Now this is 1, this is 1, and this is 1/2. And now that number works. So guys, when you are balancing thermochemical equations, you always want to balance them such that there's a 1 in front of the thing that you're given the energy for. In this case, it's carbon monoxide, so you can balance equations with fractions. Something we've never talked about before. Yeah? Well, it would be wrong if you had this. Water is not H1/2O, right? You can't have fractions of atoms, but you can have fractions of moles of atoms. Sure, you can have 1/2 mole of oxygen. It just weighs 16 grams instead of 32. Yeah, so you can have fractions of moles. You can't have fractions in chemical formulas, but you can have fractions in balanced equations. Okay, all right. So guys, here's what we're going to do then. Let's round this out. So this is the question that you'll be confronted with on the test. It would actually read like this. They wouldn't give you this immediately, but they would give you this question. And it would say the enthalpy of combustion, da-da-da-da-da, the enthalpy of combustion of carbon monoxide, da-da-da-da-da, calculate the enthalpy of combustion of carbon to carbon monoxide. This is where they would then give you these balanced equations, which again are just these in equation form. And guys, we now need to figure this out. We now have enough information to solve this problem, and we're going to do this together. This is through a process called manipulation. And guys, this is how this goes. I'm going to actually even give you steps. And you guys understand that steps don't exist anymore, right? Here are the steps for solving these by manipulation. They're not on the board. I'm going to just give them to you. You can write them down if you want. Guys, step number 1, write the subject reaction. I got it, Joel. Step number 1, guys, is write the subject reaction. Subject reaction. What is the subject reaction? Well, guys, the subject reaction is the reaction that we are trying to find out delta H for. So this is our subject reaction. It says calculate the enthalpy of carbon to carbon monoxide. So we are now going to write the subject reaction. So this is going to be carbon turning into carbon monoxide. But what's missing? What do we have to add to carbon to get it to be carbon monoxide? O2, right? Now, how do we balance that equation? Right, we should go 1 carbon, please don't do this, 2 oxygens, 1 oxygen, so we put a 2 and we put a 2. That's the way we would have done it. But guys, the question is specifically asking us for the enthalpy of combustion for 1 mole of carbon. And because we want this relative to 1 mole of carbon, we can't put a 2 in front of carbon. So instead, to balance this, we put a half here, and now it's balanced. You okay? All right. So now, guys, what we've got to do is this. And this is step 2. Manipulate the given equations so they match. Let me say it again. Step number 2 is manipulate the given equations so they match the subject equation. Do you need me to say it again? Manipulate the given equations so they match the subject equation. I'm going to switch colors. Not to sky blue. Doesn't show up so well. So guys, one more time. Manipulate the given equations so they match the subject equation. So there's 2 ways that you can manipulate equations. You can flip or you can multiply. You may want to make those subpoints under step 2. You can flip or you can multiply. So guys, let me show you how this works. So this is our subject equation, right? This is what we're shooting for. These are our given equations. And this is the way they'll set these up for you on the test. They will give you equations, and then they will somehow get you to a subject equation. Sometimes they'll just give it to you. In the homework, you'll see they'll just give it to you. Sometimes they'll give it to you as a sentence and you need to write it. But in either case, now what we're going to do, guys, is we are going to take these given equations and make them look like the subject equation. And here's how you do it. You look at your first given equation, and it's obviously the top one there, and you say, okay, the first element that I run into is carbon. How many carbons are there? 1. Is it on the left or the right-hand side? The left-hand side, and then you go down to your subject equation and you find it. So you're like, okay, this starts with carbon, here's my carbon. And then you ask yourself the same two questions. How many carbons are down here? 1. And there's also 1 up there, so that matches. Now, which side is the carbon on? Well, up here, it's on the left. Down here, it's on the left, so these match. Does that make sense? Okay, now you go to the next given equation and you ask yourself this. What do I run into first? Carbon monoxide. Where is it? It's on the left. How many of them are there? 1. Do you get the idea? Now find it down here in the subject equation. Where's the carbon monoxide, left or right? It's on the right. So what are we going to have to do to make a match? We're going to have to flip this around, and we'll do that in a minute. So we got to flip it over, but then guys, what about the numbers of them? 1 carbon monoxide here, 1 carbon monoxide there, so we're good. So this one, this bottom one, we need to flip it, but we don't need to multiply it by anything because it's already good. So guys, what we're going to do is we're going to take this and we're going to flip it over. So we're going to rewrite it as carbon dioxide yields carbon monoxide plus 1/2 O2. Exactly. That's going to be really important, Brandon, in a couple minutes. We just turned a synthesis into a decomposition. Now, guys, can we do that? Can we just take a chemical equation and flip it over? Absolutely. But what else do we have to change thermochemically? The sign of the delta H value, so that is no longer negative, it's positive. Okay. So now, guys, we have done step 2. We have manipulated our given equations so that they match the subject equation. Now, guys, step 3, add them up. That's all you got to write down. Step 3 is add them up. And what we are adding up is our given equations. So guys, let me get rid of this. So this is now gone. It has been replaced with this because we manipulated it, we flipped it, and now we're ready to add these up. So guys, here's how you do it. We've got now 2 given equations. We've got this one and we've got this one because we rewrote it when we flipped it. So now what we do is we bring down, adding up, we bring down all of our reactants. So here we've got carbon and we've got O2. So those are the reactants from our first given equation. Now we get the reactants from our second given equation, and that is CO2. So now we've brought down all the reactants. Now we bring down the products. So here as a product, we've got CO2, and then as a product over here, we've got CO, and we've got 1/2 O2. Do you see what I did? Make sure you're clear on this, guys. Brought down these reactants, and this reactant brought down this product and these products. You okay with that? Ask questions if you're not. Well, but look at where they came from. So the C, and this is going to get a little sloppy, but so let me see if I switch colors again. Let's go black. So this CnO2 came here, and then this CO2, the other reactant, is right there. Is that okay? So we brought our reactants together, then we brought our products together, CO2 and those. Does that make sense? So we're just gathering all of our reactants together and all of our products together. Is that okay? Go ahead, Rebecca. Show me where? Here? Because so the idea here is when we took this reaction and flipped it over, the CO2, did I write it wrong? Oh, no, wait. Oh, wait, ask me again. I don't understand your question. Are you looking at this guy? Okay, so where did that come from? So the big question here is calculate the enthalpy of combustion of carbon, which is this, to carbon monoxide, which is this. So it's saying how much energy moves around when carbon turns into carbon monoxide. And so to make this balance, we just had to add the oxygen. Okay. You guys good? These are great questions, guys. Pick this apart because you need to know how to do this. Okay, now we're on step 4, simplify. Be careful, they're not spectators, but a similar process. So we've got a carbon here, there's no carbon over there. We've got an O2 here, and we've got some O2 here. So we are going to cancel out half an O2. So if we cancel out half an O2, here it's gone. And if we remove half an O2, what's left over here? Half of an O2. Now, carbon dioxide exists on both sides, so we can remove it on both sides, and look at what we're left with. Carbon plus half an O2 gives us CO. And this is our subject reaction. So what did we just verify? Well, we verified that if we take these given reactions and manipulate them by flipping the second one over, then these two reactions add up to the subject reaction. So what does Hess's law now tell us? That we can take these numbers and add them up, and they will give us the energy of the overall reaction. Do you get it? See, guys, if we know the energy of this reaction, and if we know the energy of this reaction, and we do because we flipped it over and changed the signs, if these reactions circled in red add up to the subject reaction, and we just showed that they do, if these add up, then these numbers will add up to the energy of the overall reaction. So now all we got to do, guys, is add those together. And grabbing a calculator, so we've got 393.5, and that's negative. And if we add to that 283.0, and guys, why is the 283.0 now positive? Because we flipped the reaction and we add those up, and the delta H for this reaction is negative 110.5 kilojoules per mole of carbon. So guys, that is the process of manipulation. We needed to add that last step though. What were we step 4? Add them up. Simplify. Then guys, the last step, whatever number it is do the math. Yep. In this case, and this isn't the case, so don't take this too far. But guys, the other thing that you'll run into, and that was not represented in this problem, but imagine, let me go back. I'm going to switch to a disgusting color so it stands out. Yellow, green, this couldn't be worse. Imagine that this equation balanced and there was, here, let's make it worse. No, let's make it bigger. There you go. Guys, imagine, and this isn't the case, but just play along. Imagine that when we balanced this equation, there was but we couldn't do that. Hold on. Let's say this differently. Imagine that there was a 2 here. What would we have to do? Well, not only would we have had to have flipped this, what else would we have had to have done? Doubled it. And we would double this, making it 1. We would double this, but we would also have to have doubled that. So when you do these manipulation processes, it's not always just flipping. Sometimes it will also be doubling and tripling to make the number of atoms add up. You get the idea? Okay, now, thinking about the AP test and getting away from puke green, what could they have done to you on the AP test that would have been absolutely evil in terms of having you do this process?
So, like checking so that the CO2 on the first reaction is like 3 and CO2 on the second reaction is like 2. And then
You'd have to fractionally change them. They won't do that. Do you understand what he's saying? You know, when we did the math, it turned out really nice because we had, I don't think I can get rid of the puke green. I can't. But guys, realizing that this shouldn't be here. Notice that when we brought these together, we had 1 CO2 here and 1 CO2 there, and they canceled. That they will not put you in a position where you have to do relative multipliers. That would be horrible. What else could they do to make these things really nasty? Say it again. Or worse, what if they gave you given equations that were distractors and you didn't need them to add them up to the subject equation? They will not do that to you either. So guys, here's what's going to happen. When you sit down to the test, when you sit down to the AP test, if you see if you see given reactions, and if you see a question that says, find the energy for this overall reaction, your brain goes, that's a manipulation problem. I know how to do it. All I've got to do is take these given reactions, flip them left to right if necessary. That changes the sign. Multiply them by multipliers if necessary, remembering to also multiply the energy values by those multipliers. Add them up. At that point, guys, they will always add up right. They will not give you distractors, and as you said, Jake, they will not give you examples where you've got to do relative multipliers. They'll always add up. Do the math. Yeah.
So what we did was we kind of flipped that, and we put all the reactants in the product in this spot.
Yep.
But we did end up only adding 283 to 390.
Yeah. Uh-huh. Yes.
Will it always be like that?
The only thing that could change is that maybe you might have to multiply these numbers by some sort of factor to make the number of molecules cancel.
But in the end, will always just be
Yes. Yeah. Well, yes, adding them all. And that's Hess's law, is just you'll always just be adding them all up. Of course, if they're negative, functionally you're subtracting them, but you're just adding them all up. Yep. You guys good? You're okay? Okay, so guys, now we're going to shift gears a little bit. You know how to do this through manipulation. Now we are going to do this computationally through a concept called enthalpies of formation. Let's define it, then we'll talk about it. So it goes like this. You know what? Before I show you the definition, maybe if we talk about it, you'll better understand it. So guys, what is enthalpy? Heat in the absence of work. And then what does it mean when we talk about formation? What are formation reactions? Synthesis reactions. What do synthesis reactions do? They take reactants and they form one product, right? So guys, when you think about formation, think synthesis. So basically what an enthalpy of formation is the change in energy when a reaction takes place that forms 1 mole of a compound from its component elements. So hydrogen plus oxygen makes water. Carbon plus oxygen makes carbon dioxide. Carbon plus hydrogen plus oxygen makes sugar. Whatever it is, it's the amount of energy that is involved when products form, compounds form from their elements.
Would these be monatomic elements?
We're going to talk about the diatomics in a second. So guys, these then are the rules and the things that you need to understand. When we talk about this, first of all, it's abbreviated delta H naught sub F. We have not seen the naught before. So guys, I don't know if you're familiar with this, but we can talk about it now. This little circular guy is not the degree symbol. Mathematically, physically, it's actually read as the character naught, K-N-O-T, naught. And guys, the term naught simply means at standard conditions. Understand that all of this stuff, until we get into batteries in chapter 20, everything that we're going to be doing in this class is at standard conditions. So what are standard conditions? Just so you know, it assumes that the substances are pure. It assumes that they are at 25 degrees Celsius. which is 298 Kelvin, and 1 atmosphere of pressure. But bottom line, guys, you don't need to know that because everything we're going to do is at standard conditions. So, yeah. Yep. Okay, so now, guys, let's do this. Grab your books and look at table 5.3, which is what I had you open to on 184. So, guys, notice what we've got here. We've got a table of standard enthalpies of formation. Down the first and fourth columns, we've got the names of the compounds. The next column over, we've got their formulas. And then finally, in the last column, we've got their delta H naught values in kilojoules per mole. So, guys, allow your eye to scan through this table. And let's talk about some of the things that you observe. Interesting. So, guys, let's talk about negative, and then let's talk about mostly negative, and then let's talk about pretty negative. So let's do negative first. So, guys, why are most of these values negative? Which means they're exothermic, but why would you expect that? Go ahead, Matt. Why would you No. Right. Yeah, you're making compounds, right? And guys, you know this was disturbing a couple days ago, but now you're getting a little more comfortable with it. When bonds form, what happens to energy? It goes away. So guys, when bonds form, heat of formation, enthalpies of formation, when bonds form, we would expect energy to be released, so we would expect these to be negative. So now let's talk about pretty negative. Guys, look, and we don't mean pretty like beautiful, we mean like pretty stinking negative, like big. So guys, look at these values. Do you notice that the values that are negative tend to be somewhere between big and enormous? Okay? Now, let's talk about the things that we wouldn't expect. First, well, some of them are positive. What does that mean? No, because diamond actually, and diamond is one of the most stable things we know of. So guys, what does it mean that they're positive? What's going on? When these substances are formed, what's going on? Heat is being absorbed rather than released. Now guys, how can that be? And understand, and let's just talk about this. We'll talk more later, but let's just say this now. We are not violating anything that we've previously said. When a bond forms, is energy given off or taken in? Given off. Is there an exception to that? Never. Guys, there is never an exception to that. When a bond forms, energy is always given off. So if that's true, how can it be that energy is being taken in when some of these things form? And guys, a typical guess at this is people will say it's because energy is going in to break down the reactants so they can turn into products. That's not the answer. So what is the answer? Guys, the answer is entropy. And that doesn't come up until chapter 19. We're not going to talk about it now, but understand, guys, for us to understand how is it that some of these heats of formation can be positive instead of negative, it's not because magic bonds are forming that magically give away energy rather than take them in. It's not because energy is going in to break down the reactants so they can turn into products. The reason that some of these are exothermic or endothermic is because there's a change in entropy, we'll talk more about this in a couple days, that is offsetting the energy that's being released as the bonds are forming. So we're not changing anything, we're adding something that we can't talk about yet because we haven't done chapter 19. Okay? But do notice this. What do you notice about the ones that are positive with the exception of acetylene? What do you notice about these positive numbers? They're pretty small, right? And that plays into it too, and we can talk more extensively about this in chapter 19. Okay, so guys, let's make sure that you're really clear on what it is that you're looking at here. So let's take, for example, water. Go down and look in the lower right-hand corner at water. First of all, you'll notice that water is there twice. Why? One is a liquid and one is a gas. Which one has a greater heat of formation? Yeah, you'd think the gas would, right? But why is it that the liquid has a greater heat of formation? What has to happen in order to turn a gas into a liquid? Heat has to go away or go in. If you've got steam and you want to make it liquid water, what has to happen? Energy has to go away, right? And so the idea, guys, is the difference in energy between the formation of liquid water and water vapor, gas, steam. The difference between those is the energy that has to be lost to turn steam into liquid water, because some energy has to go out to turn it into liquid water. Does that make sense? Okay, but guys, let's just look at the bottom one, at water vapor first. So what on earth does this mean? And you may want to write this down with me just as an example. So guys, what do these numbers mean? Well, here's what we've got. We've got the delta H sub-naught formation, and that is for the bottom one. Let's do the gas. What's the number there? I guess I can look it up. Negative 241.8. And that is kilojoules per mole. But it's mole of what? Guys, it's mole of water. So what that means, and that's water gas, what that means, guys, is when a mole of steam is made, 241.8 kilojoules of energy is given off. Does that make sense? You're okay with that? So guys, what does that look like? Well, let's come over here and let's write the balanced equation. So this is for 1 mole of water. So now, guys, the question is, what goes into making a mole of water? Well, what is water made of? Hydrogen and oxygen. So this is hydrogen plus oxygen. But here's the problem. You guys know that hydrogen and oxygen don't exist by themselves. What do you remember about hydrogen and oxygen? They're diatomics. So this is a 2 and this is a 2. Now we need to balance it. And now it balances, so there's still a 1 in front of the water. You get the idea? So guys, this is what that means in the data chart. So when it says the heat of formation of gaseous water is negative 241.8 kilojoules per mole, that means when 1 mole of hydrogen gas reacts with half a mole of oxygen gas to make 1 mole of steam, 241.8 kilojoules of energy comes out. Do you get it? Is that okay? Do you understand what this table is representing then? So guys, now let me ask you a question. What molecules, given what we just wrote on the board, guys, what molecules are not on the table? The diatomics. You'll notice that it doesn't have the heat of formation for H2. What would that look like? Well, it would be H plus H yields H2. It doesn't have the heat of formation of O2. O plus O yields O. Why are they not on there? Guys, the reason that they're not on there is because they're spontaneous and they don't exchange energy. Oxygen does not exist as individual oxygen atoms. You never see oxygen hanging out by itself because oxygen will bond to oxygen and will make O2 with no exchange of energy. That bond forms spontaneously, and because it doesn't require an energy change, it always exists like that. So you don't see the heats of formation for the diatomics because you never see them any other way, and those energies are understood to be 0. So when you read this table, let's just say it in word form, guys, all of the diatomic elements are understood to have heats of formation of 0. Meaning that energy is not necessary for oxygen to turn into O2, which explains why we only find oxygen as O2. Conversely, right, in either direction, energy is not exchanged. Whether O2 is breaking apart into O's or whether O's are making O2. Remember, they're reflexive, but plus or minus 0 is still 0. Yep. So why does it exist as O2 and not O?
No, I'm saying like what you consider
Yeah. 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 Uh-huh.
Right.
Yeah, so what's going on? So why is it when O plus O makes O2? There's an offsetting change in entropy that cancels it out. Exactly. Yeah. And we're...
We don't know it.
You don't know. We're not talking about nothing we know. Yeah, no. Go ahead. Yeah, no. So, guys, okay. So entropy is disorder. And so what happens is that when O plus O makes O2, there is some energy given off because a bond is forming, but the amount of energy that's given off is offset by the amount of disorder that's decreased. Because two oxygens are more disordered than oxygens bonded together as O2, and they perfectly offset each other. But we'll talk more about that in chapter 19. Okay, I know. Poor Brandon. All right. So, guys, you okay with these ideas? And you understand now that what these numbers represent in the table is the formation of a compound from its representative elements. Is that okay? All right. So now, guys, check this out. This is really cool. You're going to like this. Going back to what we learned about before, manipulation. You ready? Write these down. Center them and skip a line between each one. Don't write down the words. I want to get rid of the words. It's still under computation. I'm going to move this up. Look at me being all moving stuff. Okay, here we go. We're skipping lines. We're doing business. You're going to want some white space to play with these. Guys, you understand that one of the reasons that I love to teach is because I'm always learning things. It was about 5 years ago when I was teaching this stuff, where I had this aha moment that calculating delta H's by heats of formation is exactly the same as calculating delta H's by manipulation. It's just easier. But what I'm going to do is I'm going to teach you how to calculate delta H's by heats of formation by doing it through manipulation, and then show you how the two fit together. And you're going to have sort of an aha moment. So do you guys all have your AP cheat sheets, your equation sheets nearby? Okay, all right, do this with me. So guys, don't turn your attention to the equation sheets. Play along with, have you all got these written down? Okay, so check this out. This is pretty cool. So here's how this goes. You're sitting down to the AP test, and you see a question on the AP test, and you've got a subject reaction, and you've got a bunch of given reactions, and your brain goes, what kind of question is this going to be? Manipulation. And so now you're saying to yourself, when I solve the manipulation equation, what I need to do is compare my subject or my given reactions to my subject reactions, and I need to manipulate these reactions so that the givens match up with the subject, and once they do, it should all add up, and I can do the math and come up with the delta H for the subject reaction, right? Okay, so guys, let's do this together. You ready? So here's what we do. We look at our first subject reaction, and it's got carbon in it. But we don't have carbon in our subject reaction. So what do? Nothing, we can't. Then we've got hydrogen in our given reaction. Where's hydrogen in our subject reaction? It's not. We can't do anything with it. Now we've got CH4. Is CH4 in our subject reaction? It is, but what's the problem? It's on the wrong side. So what do we do with our given reaction? Flip it over. So let's do that. Let's rewrite it. So it now becomes CH4 yields C plus 2H2. So we flip the reaction over. But when we flip the reaction over, what else do we have to do? Change the charge, it's not really a charge, change the sign of what? The delta H. But we ain't got a delta H.
That's a problem.
But we have a solution. Guys, check this out. What kind of reaction is that? A synthesis reaction. Do you see that this is actually the reaction, the equation that represents the formation of CH4? So can't we find the delta H for this reaction simply by... See what I'm saying? Okay, so what is that value for CH4, which is methane? Negative 74.80 kilojoules per mole. So the delta H for this reaction is negative 78.40. Forgive me for not putting kilojoules per mole. But guys, realize it's negative 78.4 kilojoules per mole for the formation of CH4. Did I write it down wrong? Oh, sorry, a little dyslexic. No, you have to memorize them all. No, I'm kidding.
I dropped the flag.
Yes. No, and actually, so guys, Rebecca's question is good, and actually the answer is no. They tend to not give you data in large tables. What they tend to do is give you the specific data you would need for this question. But they would give you the data. 74.8. Okay, so yes, and that's what we need to talk about. So negative 74.80, again, forgive me with the units. But guys, again, make sure you're clear on this. 74.8 kilojoules per mole is for the formation of methane. But what did we do to that formation reaction to make it fit our subject reaction? Flipped it over, so what do we do here? Switch the sign, so this becomes positive. Okay, so now guys, let's do this. So we look now at our next equation, and let's talk manipulation first. So we've got oxygen and oxygen, but we don't have any oxygen. Hey, it doesn't matter. It's all qualitative. Yeah, use that. Yeah, for sure. So, so guys, no oxygen. We've got oxygens on the left, but none up here, right? So what do? Don't worry about it. But then, guys, we've got O2 on the right, but where is it up here? It's on the left. So what do we have to do? Flip it over. Let's talk. So now we've got O2 yields O plus O, and then the delta H of this, and we look up the delta H, the heat of formation for oxygen. It's not there. It's because it's 0. Right? Okay, now guys, you've got to do a little bit of looking ahead. Because you may be thinking to yourself, wait a second, now I've got one O2, but there's two O2s. But if you glance down at the next equation, you'll notice that your second O2 is right here. So what if you hadn't done that? Guys, what if you had done this, and what if you had gone 2 and 2 and 2 to give you the two O2s that you need? Well, what you would have found then is that when you added that up, you would have had too many oxygens, and you would have gone back and said, oh, where's my mistake? And then you would have gone, I've got an oxygen, an O2 from here. I don't need those two O2s there. And you could have gone back and cleaned it up. Okay, now guys, continuing on, look at this equation. Carbon on the left, carbon in the equation, oxygen on the left, oxygen on the left, CO2 on the right, CO2 on the right, and do we have the correct number of them? 1 CO2, 1 CO2, so we're good. So guys, what manipulation do we need to do to that third equation? None. So all that we need then is the delta H value, And the delta H value for the formation of carbon dioxide is negative 393.5. And I'm going to stay consistently bad and just not put units. Okay. Now, guys, let's check this last one. Hydrogen in our subject, in our given reaction, hydrogen here. Oxygens. Are we okay? Oxygens were good. What about waters? They're on. Are we good? What do we got? We've got 1 and we've got 2, so what do we need to do? We need to double it. So guys, we're going to double it. We're going to go 2, and this then becomes 1, and this becomes 2. And let's say that this is steam. They should have told us that it's the gas form. But now, guys, we've got this number, negative 241.8. We got to double it. So the delta H for this now is negative 482, 483.6. Okay. Oh, I did it again. I'm so used to doing it right. Okay. So now, guys, we got to do some error correction. As we do this, we understand that we're going to need 2 O2s remaining, right? So let's look at what's going to happen as we bring this down. Because we flip these over, we've got 1 O2, 2 O2s, 3 O2s. Do we have any O2s on the other side? Are we okay or are we in trouble? So this is clean. Here we've got O2s. Here we've got O2s. What's that? No, I know we've got 3 O2s on the left. And we've got any O2s on the right? No. It's got to be O2. Yeah, and you know what, guys? It's interesting. This is really interesting. I did this last year and we didn't run into this impasse. So let's think about this. This is really interesting. Okay, so that's really interesting. No, I know, and that's actually the trick, but the problem is given what you guys know about manipulation, that's interesting. This is actually an example that's going to require a simplification that could blow your mind. Well, we will. See, so do you guys understand the problem that we've run into? These actually do not sum properly. Because here, don't write this down with me, but let's just make sure you understand the problem. So if we do this in black, and when we bring these down, we would end up with CH4 plus O2 reactants plus C plus O2 plus 2H2 plus O2. Are those all of our reactants? Did I do it? So we've got CH4, we've got O2, we've got CO2, 2 H2s and an O2, and then our products would be C, 2 H2s, and then an O and an O and a CO2 and 2 H2Os. Did I do that right? Is that correct? Okay. So now, guys, when we simplify, we've got a carbon that goes, We've got two H2s that go. And do you see the problem? We've got 1, 2, 3 O2s over here, and then we've got these hanging oxygens over here. I need to go back and watch the screencast from last year because some reason my class last year didn't get to the point where this fell apart. But guys, I'm just going to have to go deep with you and explain to you why this still works. Okay, so guys, listen carefully here. So we're going to do a moment to help you understand why this is still okay, but then we're still going to get to the important application of this in a second. So guys, if you turn your attention here, how much energy is gained or lost when O2 turns into two O's or two O's turns into O2? None. Consequently, can I use the word consequently with you? Because no energy is gained or lost, these two are technically interchangeable. And because these two are technically interchangeable, we can do this, and then it all adds together. Okay? Now, guys, with that said, I know that some of you right now are going, oh my gosh, then what does that do to the way I'm going to solve manipulation problems on the AP test? And the answer is don't worry about it. They will not give you an example where you need to understand that those are interchangeable because the delta H is 0. But given this situation that I'm running you through, and again, I'm really curious to see how you guys talk me through this differently this year than last year, because last year we never ran into this impasse. And I'm really curious to see what happened differently. But you sort of now understand this idea that they're interchangeable because delta H for that is 0. Independent of that, guys, what I want to, and so are you then convinced that this adds up and it gives us the overall reaction? Is that okay? Can we all at least agree on that? If you don't, even if you aren't comfortable with this interchangeability, let me put your concerns to rest. You won't be placed in that position on the AP test. But you do need, before we can move on, you've got to be comfortable with the idea that going through this manipulation allowed this to add up to this. Are you okay with that idea? Okay, so guys, with that underlying understanding, I'm now going to move forward because we can still get to the really interesting part of this, and we're going to do it right now. So don't miss this because you're confused about the other. Can we go forward? Is that okay? Okay, so guys, what do we need to do now to figure out delta H for this? What have we got to do? We've got to add these numbers together, right? We've got to add the two numbers in blue and the two numbers in red, and that'll give us the delta H. Does that make sense? You're okay with that idea? Okay, now guys, watch. This is the part that you can't miss because this is cool. Check this out. I'm going to go, we're going to go red. Okay, so guys, here's the idea. Did you notice that these reactions require two different types of manipulation? What do we have to do to both those first reactions? Flip them over. But guys, notice this. This was the heat of formation for CH4, and this was the heat of formation for O2. And both of those we had to flip. But guys, where is the CH4 and O2 in our subject reaction? They are reactants. Now guys, think about this. In a reaction, are reactants produced? In a reaction, are reactants produced? No, they're consumed, right? So guys, does it make sense that if these are heats of formation, and if these are reactants, that because reactants are not formed, because reactants are consumed, we'd have to flip them over? Does that make sense? So guys, these are both reactants. And because these both represent reactants, we had to flip them over because reactants are not formed, they're consumed in reactions. But now guys, watch. When we flip them over, what did that do to the math? When we flip these over, what else did we have to change? We had to change the signs of them, right? Because these substances are not produced, they're consumed, and the original values were the heats of formation. So what we really needed are heats of consumption, because reactants are consumed rather than produced. Does that make sense? Then, guys, what else did we have to do? Well, we also had to multiply this one by 2 to make the numbers line up. So, guys, fundamentally, look at what we did. To make all of this math work out, the first thing we had to do was flip, because they were the reactants. So we flipped, and when we did, we had to change the sign. Then we still had to multiply these by numbers to make them add up. And once we'd done that, flipping the reactant equations over and multiplying by numbers, they all added up and we did the math. Well, guys, guess what? That whole process is on your AP equation sheet. Go grab your AP equation sheet. Do you see it? You see it, guys? The third equation down under thermochemistry. Here's what it says. It says this. It says delta H naught is equal to the sum. And what does sum mean? Add them up. The sum of the delta H's formation of the products minus the sum of the delta H formations of reactants. Now, guys, remind yourselves, check this out. When we did the math, what did we do? Well, what did we have to do with the heats of formation that were for the reactants? What did we do to their signs? We flipped the equation, so what did we do to the signs for the delta H's? Switched them, we made it negative. Guys, that's what this does. We are subtracting the heats of formation of reactants, because reactants are not formed. It's the heat of formation. But guys, reactants are not formed. Reactants are consumed. So we subtract those values, which functionally makes them negative. Then what else did we need to do? Well, we needed to multiply these things by the number of moles of each one of them, which is why we multiplied this and this and this by 2. And guys, you'll notice that that is not on the AP equation sheet, but it is in the book. So let me show you the way that this looks in the book. It actually looks like this. I would encourage you to write this down. It says this, the delta H naught for the reaction, and this is exactly how it is in the book. I like this form better. So the heat of reaction, the enthalpy changes delta, the change in enthalpy for a reaction is equal to the sum of N. And what is N? The number of moles. So it's the number of moles of our product's heats of formation minus the sum of the number of moles times the heats of formation of our reactants. I am still really curious to know what happened with that, where those didn't cancel right. We understand why, but why didn't we run into that last year? You got it? Okay, guys, let's use it. So it says this. It says, calculate the standard enthalpy change for the combustion of 1 mole of benzene to carbon dioxide in water. Here's the equation, but we need to balance it. Tell you what. Let's just let me do this because we're almost out of time, and then you can pick it up if you need out of the notes. So when we balance this, we get 6, and we get 6, and we get 6 hydrogens, so we need a 3. Now, guys, how many oxygens do we have? Did I do that right? So we've got 12 plus 3 is 15, but guys, that's not going to work, right? So you understand that we've got the odd-even conflict, so we've got to come back and double and go from there. Yeah? Yeah. Not bad, huh? That's actually how you balance this equation. And guys, the reason is because we're trying to calculate the standard enthalpy change for 1 mole of benzene, so it's got to be a 1 in front of the benzene. So that's actually how you balance it. Okay, so how do we do this? You ready, guys? Check this out. Write this. Do you want to write it? Okay. So here's how you do this. Delta H for the reaction is equal to the sum of N times the delta H of formation of products minus the sum of N times the delta H naught formation of reactants. Now you move all the way over here. Delta H naught for the reaction is equal to, and guys, it's products minus reactants. So it would be the quantity 6 times the heat of formation of carbon dioxide plus 3 times the heat or enthalpy of formation of water. That quantity minus 1 times the heat of formation of C6H6 plus 15 halves the heat of formation of O2, which thank goodness we know to be 0. Now guys, what do we have to do? Plug in the values for the heats of formation of carbon dioxide, water, benzene, and then the heat of formation of oxygen, diatomic oxygen is 0, and then you just do the math.
What is delta HF?
Delta HF is the heat of formation. If you look at the top of the table that your book's open to, that is the abbreviation for the heats of formation. So that's,
Delta H naught.
yeah. Oh yeah, so delta, it should have the naught. It just means standard temperature. Do you get the idea, y'all? And you can do the math on your own. All right, so you guys already have the homework in front of you. We wrote it down last time. We're going to finish that assignment and grade it on Thursday. Guys, as you're wrapping this up, this will come back in just a second.